Hello, my name is Mincho Kim, and I will be presenting a work titled Cluster and Aggregate with an Application to Face Recognition with Large Probe. The scope of the paper is in feature fusion, and the application is on the video-based face recognition because the task entails few traits that make it challenging. First, the frames in the video are of varying quality and identifiability. Some are more useful than the others. Frames can vary and be very large in number. In IJBS dataset, some probes contain over 1 million frames. In live setting, the frames come in sequentially. This raises an important question of how to utilize the past frames when one new frame is added. Given a set of features representing each frame, one must be able to fuse them into a single feature for a recognition task. The task is called feature fusion, and our method proposes to handle all these scenarios. The most intuitive way to perform feature fusion is to do averaging the features. But since some features are better than the others, some works perform quality estimation. But the problem with this approach is that the intra-set relationship among the samples are not considered. In other words, each sample does not consider the quality of other samples. The model can take all inputs at the same time. One example is an attention mechanism, which by design can model intra-set relationship. However, when n becomes too large, the computation becomes infeasible, making the model impractical. We propose a new two-stage paradigm. First, the inputs f1 to fn are arbitrary number of inputs. Secondly, we cluster them into a fixed number of intermediate features. Then the subsequent aggregation network takes the intermediate features to produce a single fused output. What benefit does this two-stage paradigm bring, one might ask? And the motivation of the two-stage paradigm is in creating a rich intermediate representation that summarizes the inputs. This is very useful for dividing the input stream into batches. For instance, consider this queue into smaller batches. The first 4 samples are clustered into 3 intermediates. Could be discarded, and the next 4 could be fed in and update the intermediate. Last one. Then the summary intermediate could be used to produce a good fused output. Then one might ask, isn't this similar to the recurrent module and be susceptible to the input order, meaning that the contribution of early inputs? To avoid this problem, we propose an architecture for the intermediate representation that can be updated with a batch order invariant rule. Overview of the whole pipeline. It comprises of 3 components: style input maker, cluster network, and aggregation network. Each component will be explained one by one. We use pre-trained feature extractor to map individual images to a set of features. Extract style vector from each image, which will be useful for determining the quality of each prediction. The style vector is defined by the nonlinear operation on the mean and variance of intermediate features. Secondly, the style and intermediate features are clustered in using cluster network. The purpose of the cluster network is to soft assign the styles and identity vectors of length n to a fixed length m. We learn a global and shared cluster centers whose similarity with style governs the assignment of features to each cluster. Then the resulting m intermediate features are given to the aggregation network to produce a single fused output f. Aggregation network maps a fixed shape features into a single vector using few MLP layers. When one has to perform sequential inference, we store the previous intermediate outputs and update them with new ones. The update rule is weighted average of weights from an assignment map. This update is batch order invariant. For training, we use 2 kinds of losses to train the whole thing end to end. First, we use a simple cosine similarity between the fused feature and the class center. Secondly, we further add a permutation and variance loss, which induces the fused output to be order invariant. We compare our method with other feature fusion methods. Naive is simple averaging. PFE and CFAN, which are single image weight estimation methods, and RSA, which is an attention mechanism. The chart shows that the relative performance increase over the simple averaging, and it shows that cluster and aggregate outperforms other methods in various datasets. Note that the gap increases with increase in probe set size, which shows the importance of proper feature fusion when n is large. Lastly, we show speed and memory usage. The relative FPS of fusion stage is 120 times faster than the feature extraction stage, making the module very practical in terms of its usage. Also, our method supports very large n set size, whereas RSA, using an attention mechanism, fails with n over 184. And our method supports sequential inference. For more visualization and analysis, please visit our poster or refer to our paper. Thank you.